The Vera Rubin Observatory in Chile just found something impossible. An asteroid the size of a city block should not be able to spin faster than the blade of a kitchen blender. And yet, 710 meters wide. Wider than the Eiffel Tower is tall. One just did. Something out there is breaking the rules we wrote for how rocks are supposed to hold themselves together. For decades, we've watched space the way you'd watch a photo album. One still image at a time, taken years apart. That's about to change. A new telescope in Chile just started filming the sky instead. And in its first year of footage, before the real filming even began, it already caught things that shouldn't exist. The telescope is the Vera Rubin Observatory, jointly run by the NSF and the Department of Energy, perched at 8,800 feet on a Chilean mountaintop. On June 30th, 2026, its director, Bob Bloom, called it amazing and humbling to finally begin the mission after more than 2 decades of work. What they switched on that day wasn't just a camera. It was the start of a 10-year, continuously running record of the entire universe changing in real time. Here's the idea in plain terms. Most telescopes take a photograph. Rubin takes a movie. Its camera, the largest digital camera ever built, at 3,200 megapixels, snaps a new image roughly every 40 seconds, all night, every few nights, across the entire southern sky for the next 10 years. Over that decade, it will revisit the same patch of sky around 800 times, layering exposure on exposure until faint objects invisible to every telescope before it start to emerge from the noise. Think of the old approach as flipping through a family photo album, with decades missing between pictures. Rubin is a security camera running non-stop over the whole sky, and it never blinks. Anything that moves, flickers, explodes, or vanishes gets caught. And the system is already flagging millions of changes every single night, each one a tiny ping saying, something here just wasn't the same as it was a few nights ago. The strangeness started before the mission even officially began. Back in June 2025, during early test observations, Rubin pointed at a well-studied patch of sky called the Virgo cluster. Galaxies astronomers have been photographing for 100 years. In that single test image, it counted around 10 million galaxies. And tucked into the corner of the frame was something nobody had ever seen. A faint ribbon of stars, stretching 163,000 light-years, roughly the width of our entire Milky Way, trailing off the spiral galaxy Messier 61. It's the wreckage of a smaller galaxy, torn apart and smeared across space, sitting in plain sight the whole time. That should have been the headline of the year. It wasn't even the strangest thing Rubin found that month. Because while astronomers were still marveling at that stellar wreckage, a team led by astronomer Sarah Greenstreet at the University of Washington was combing through Rubin's early asteroid data. And they found 2025 MN45. It's 710 meters across, and it completes a full rotation every 1.88 minutes. That's the fastest spin ever recorded for an asteroid that size. Most asteroids that large are what astronomers call rubble piles. Loose gravel held together by nothing but gravity, like a pile of sand barely resisting a breeze. Spin something like that fast enough, and it should simply fly apart. Greenstreet put it plainly. This object needs the structural strength of solid rock just to survive its own spin, which raises an uncomfortable question. What is this thing actually made of? The leading idea is almost as strange as the object itself. 2025 MN45 might be a surviving fragment of a planetary core. The dense, compressed heart of a world that formed and then shattered billions of years ago, back when the solar system was still a demolition derby of colliding rock. It wasn't alone either. In that same batch of early data, Rubin's team flagged 18 more fast rotators tucked among thousands of newly discovered asteroids, objects so small and so quick that no survey before Rubin had the speed or sensitivity to catch them spinning. If that theory about MN45 holds up, we're not looking at a rock. We're looking at a piece of a dead planet's skeleton, still tumbling through the asteroid belt 4.5 billion years later. But that's not the only impossible thing hiding in Rubin's data. Rubin also started catching something even rarer: stars that don't explode, they just disappear. In February 2026, researchers led by Chile at the Flatiron Institute confirmed a second-ever candidate for what's called a failed supernova, this one in the Andromeda galaxy. Normally, when a massive star runs out of fuel, its core collapses and triggers a violent explosion. But this star, once one of the brightest in Andromeda, simply dimmed over years until it vanished from view entirely. The theory: its core collapsed straight into a black hole with no explosion at all. Dee said it plainly: a star that basically died, and nobody noticed for 5 years. Rubin, built to catch exactly these kinds of faint, silent disappearances, is now hunting for more of them across the sky. That should have settled what Rubin was capable of. It didn't. Because the most unsettling discovery wasn't something Rubin found while it was looking. It was something Rubin had already caught and didn't even know it. On July 1st, 2025, an interstellar comet was discovered, screaming in from beyond our solar system. Astronomers named it 3I/Atlas. Only the third object ever confirmed to have come from another star system entirely. But when researchers went back through Rubin's archives, they found something nobody expected. Rubin had already photographed it 10 days earlier, on June 21st, before anyone on Earth knew the comet existed. The telescope had captured our first ever glimpse of an interstellar visitor, and simply didn't tell anyone, because nobody had asked yet. Think about what that means for a second. Somewhere in Rubin's growing archive right now, there could be another interstellar object, another vanishing star, another impossible asteroid, already photographed, already sitting in the data, just waiting for someone to go looking. And that's the real point of this mission. It's not named after a place or a president. It's named after Vera Rubin, an astronomer who, in the 1970s, measured how fast stars orbit the edges of spiral galaxies and found they were moving far too fast to be held in place by the gravity of everything we could actually see. Something invisible had to be holding those galaxies together. That measurement became one of the first hard pieces of evidence for dark matter, a substance we still can't directly detect, even now, half a century later. Her namesake telescope was designed to pursue that mystery on a scale unlike anything attempted before. Over 10 years, it will map the light of billions upon billions of galaxies. Astronomers expect the final tally could reach 20 billion, measuring how their light has stretched and reddened on its way to us. And it will track roughly 250,000 exploding stars, called Type 1a supernovae, every single year. Because those explosions burn with a brightness so consistent, astronomers use them as cosmic mile markers. Line up enough of them, across enough of cosmic history, and you can start to answer a question we still can't settle. Is the mysterious force pushing our entire universe apart dark energy, a fixed constant? Or is it changing, year by year, galaxy by galaxy, as we watch